Okay. Thank you very much, Christos.
Okay, thank you.
Thank you. Our next presentation will be online from Southeast
European University.
Yes. Menon Selimi. Thank you.
Okay. Can you allow me to share the slides?
The sharing has been enabled the whole day.
Yeah, the other participant needs to close it, I guess.
Oh, yeah. Go ahead.
I guess you can see the screen now. Can you see my screen now?
Yes, we can see a screen.
Now it's, I guess, full screen, right? Okay. Hi, everyone. My name is Menon, and I'm representing Southeast European University. I'm researcher and professor in computer science here. And this is a joint work with my student Leonard and Professor Adrian here at Southeast European University. Our PAE has to do with the machine learning at the edge, and the title of this PAE is Federated Mesh, which is like federated learning for medical data sharing in mesh networks. I'm going to explain what we have done so far and what we are doing and what is federated mesh. As you know, we nowadays, like the IoT devices, they produce lots of data, and this data is super important because it helps us to create smarter models. And in terms of the data that we are these devices are producing, the type of data that is like super interesting for us is medical data, and at the same time sensor data, which is coming from the different sensors like in smart agriculture and so on. One of the problems that we are facing here is like not the problems, but most of the modeling, most of the training of these models using this data that is coming from the IoT devices is done in the cloud. So one question that we ask, what about at the edge? Can we train the models at the edge, taking into consideration that we are dealing with low power machines and resource constrained machines? So yes, one of the things we can do machine learning at the edge, and one of the really let's say fascinating new terms that Google invented was this federated learning. So it's a type of distributed machine learning that you can do it at the edge of the network. So instead of training your model at the cloud, you can have different clients, which are like mobile phones or like small PCs or resource constrained Raspberry Pis, Arduinos, which can train your model. So instead of training the model in the cloud, you train in the clients in a different epochs, where epoch is number of iterations that the client is training. And at the end of the training, the client sends this model to the server. Server is like merging all these models and is sending a big model, which is like really, in terms of accuracy, is really good. So this is what the federated learning is doing, and we thought of using federated learning in the experiments and in the edge learning. But one of the problems, like, okay, you have this super nice technology to use it, but one of the problems that you are facing is like training takes a much longer time on a single board computers like Raspberry Pis comparing with the cloud, and which is a very super normal. And as you can see in the first graph on the top, often all cores of CPU are consumed, which leads to the reduction of quality of service. Like just training a simple model in healthcare with the healthcare data, it more or less it consumes like 400 CPU, means like 4 cores of CPU were already like consumed. This is one problem. And the second problem is like, well, we know that epochs, which is like number of iterations, is causing the CPU to increase a lot. What we can do is like, let's try to do parameter tuning. Let's try to play with a number of epochs. Maybe if you increase the number of epochs, you will increase the accuracy, the prediction rate, right? But also this is not the case, because if you increase the epoch, as you can see on the bottom figure, from 1 to 2, 3, it improves the accuracy. But when you increase to 4, basically it reaches the maximum 94% accuracy, prediction accuracy. But when you increase more than 4, this doesn't mean that it goes over 94. It can go down. It can go down, which is like the case with the epoch 8, which is 90%. So the solution is like, let's try to do something super practical, not something that someone else hasn't done it, but something practical that is going to work on the resource constrained machines like Raspberry Pis. Let's come with some algorithm which is like trying to find what is the best epoch, what is the best epoch, which is like number of iterations the client needs to train the model. Okay, we can find the best epoch, but we need to sacrifice a little bit of accuracy. But of course, it's better to sacrifice a bit of accuracy rather than sacrificing the CPU, which blocks and destroys the machine. So we created this BPOC, which is like it's implemented fully in a Raspberry Pis, and it goes over some phases, which is like training the model and doing so on. So in terms of the testbed we created here at SCU, our own testbed, more or less with 16 Raspberry Pis, which are like located in different parts of the campus. And what we see here is like we have these nanostation machines to build wireless mesh network. These are like machines to build like long range point-to-point links up to 10 kilometers between two regions, right? So 8 Raspberry Pis are located in one side and 8 in other side, and then basically they communicate. And in each cluster of the Raspberry Pis, one is the server, and all other nodes are workers, which are training the models, right? And of course, we have a green testbed because some of the Raspberry Pis are using the solar green energy that is coming from the solar panel that you see in the photo. In terms of the data set, we use like this electrocardiogram data set from the MIT data set, which is very famous, and it is using more than 26,000 of samples. Basically, what it's doing is like different patients that have heart problems. Basically, it's classifying the prediction into 5 arrhythmia diagnoses, like normal beat or left part of the heart has some problems, right part of the heart, atrial premature contraction, and so on. So what we do is like we give this data set to the Raspberry Pis, and they distribute the data set, and what they try to do is like they are coming with some prediction. And here, I mean, we try to compare with the optimum. What is the optimum prediction rate, which is like optimum that we see in the pictures, and with the yellow color is the BPOC, which is more or less we are close to the optimum. And at the same time we are coming close to the optimum, but at the same we do not sacrifice the CPU and the other parameters that can block the device. So here this is like a more or less the one set of the results for each round. Round is like one round means like once I'm training the model in Raspberry Pi, I'm sending this model to the server, and this is one round. So we are using more or less 100 rounds, and for each round, basically we find what is the best epoch. Here with the yellow color, you can see that the round, in the 50th round, we have found that the number of best epoch, and the accuracy 97%. Okay, we have a better accuracy, which is this one at 90. But it's better to use less epochs and less CPU rather than just having a better accuracy, which is like more or less you sacrifice a little bit of accuracy, but you improve the CPU and so on. So as a conclusion, what I would like to say, like the clients and the companies are asking some kind of mechanism to do machine learning at the edge. Yes, of course, cloud is the best place to do the training of the machine learning models, but sometimes the data that is coming from the sensors, the data that is coming from the edge devices, you need to train them at the edge and not in the cloud. So BPOC was something very practical, which showed a bit like the nice and good results that can be applied to different use cases. And this is a medical use case, but of course, one of the things that we are trying now is also the smart agriculture, the data that is coming from the sensors in the fields and so on. Basically, this gave us a practical insights, and this is like just a feasibility study that you can run machine learning at this low resource constraint machines. So this is between the two actors here is the Southeast European University and the Appsteller, which is like Appsteller is a company which is working on the cloud and DevOps thing, and basically they do machine learning at the cloud, and then now they are interested to do machine learning at the edge. And this was the first technology that we wanted to provide to them, and we showed that it's feasible to do this. This is my this is the conclusion. If you have any question, please. Thank you.
Thank you very much. Are there any questions? Yes.
Thank you for your presentation. I would like to ask something regarding the resilience of these kind of systems to situations where some of the nodes or devices is not working, or that you have a problem in communication. So what were some kind of strategies you would use in such cases?
That's a very good question. Thank you. Because this is like a federated learning, a distributed machine learning thing. If one of the workers is not working, basically stop working for a moment, and then it's becoming online again, or it's not working at all. Usually that node, after when it becomes online, he can get updated with a new model from the server. So basically, comparing to traditional machine learning, this is fault tolerant because you have many servers around. You have 8 nodes, worker nodes that are training the model. And in each round, the worker node, the server node is like updating the clients. But the question is like, what if the server goes down? Because that's the guy that is sending this merged, this latest model to the nodes. Then that's a single point of failure. Basically, that's a problem. But if the clients are going offline or going down, that would not be a problem because they have their own trained model in the local CPU and local PC. So that's not going to be a problem because they can get updated from the server very quickly. But if the server is going down, that the main server that is updating, that's going to be a problem. Because they will not be updated with the latest, the best accuracy. They will have some model, but they will come with some prediction, let's say, but that prediction would not be the best prediction because the best one is the one that the server is sending to them. I hope I answered your question.
Thank you. Any more questions? Okay, thank you. Our next presentation is from Faculty of Technical Sciences in Novi Sad, Branko Brkjac.
Welcome everyone. Thank you for coming. Our presentation today will be related to our internal Pathfinder experiments, but I will try to put out some ideas and things we encountered during considerations how to use spatial artificial intelligence in as a tool for collecting useful information that could be used in something that's today called digitized agriculture. Actually, it's an old idea. We would like to collect some information that would be useful for different things, but in this context, this kind of information should be something that we call spatial information, and in the context of spatial AI, we are mostly interested in visual perception of some complicated 3D environments. In the agriculture, there are many environments depending on the application and the field of use. But something that's common for all such systems or designs is that in case of spatial AI, we would like to learn some optimal signal representations to do some continuous capturing of right information that would be useful for us. And we would like to have systems that work real time, have real-time interpretation and action capabilities. And in this Pathfinder experiment, we were mostly focused on vision systems. So that will be the main topic of this presentation. So what kind of information we would like to collect and what would be some kind of technical problems we would need to solve in this case. We would like to have some multimodal information about our crops or some other vegetation that's present in agriculture. And there are different kind of devices we could use to collect this kind of information. We could use some high resolution optical imaging. In this case, we could use cameras that work in visible or some other parts of the spectrum. But there is also a question, should we use passive sensors like optical cameras or some active sensors like LiDARs in order to collect as much of that complex 3D environment? Then there is also a question of cost and how much these sensors could be used in some areas. Then we would like to have some on-site processing. Today, it's popular to say that your processing boards or equipment is on the edge. So it means that the processing happens at the place on site or nearby. And in this case, there is a question, should we have some cheap devices that could be used in some crowdsourcing, so given to many people, or we should rely on some devices that are more expensive and that could be used only in several test beds or test sites. Today, trend in spatial AI is to have embedded platforms and to have embedded vision. So it means that you have integrated cameras, sensors or acquisition devices together with processing boards to have a low power consumption, and also to have different kind of capabilities like stream processing, hardware encoding, heterogeneous computing, so that you can tailor the device to the specific need you have in order to solve some relatively complex vision problem. On the other hand, you again have some kind of question. Should we have some highly optimized algorithms and reconfigurable hardware? I would say yes, because it's more efficient. But then on the other hand, these kind of devices require some kind of expertise to use. On the other hand, you have devices that are not so smart and that are some single-purpose platforms that could be cheaper and that could be used more efficiently by more users. And at the end, when you consider how you can collect this kind of information, you can put a question, should we combine different platforms? There is no one answer. Like you could use different platforms in order to have more precision, like it's shown on the figure. For example, the simplest kind of information you could collect about 3D environment is depth perception. So better depth maps, more precise and accurate, could be achieved with combined platforms that have more processing power. But on the other hand, then these platforms are more expensive and probably use more power. So depending on application, you will need to choose what you need. And this here we come to the other side, to the next slide, where we have three kind of pillars that should be investigated in order to design some efficient system. So first, we should search for some kind of solutions that are already there in a vision community. Vision community has traditionally been oriented towards indoor environments, but today vision is more and more oriented towards outdoor environments and uncontrolled environments. And in this case, we would like to search for some kind of 2D and 3D vision solutions. And we should always consider a trade-off between level of details we need and amount of resources that are needed in that case. But as we had in the first session today, in the morning, there was a presentation of DigiPlant. I think that was the name of the solution. The presenter told us that there is some expert knowledge and there are some solutions that are there on the shelf, and that it's not so easy to combine these together. So the next pillar that you see on the slide is actually to find not only some existing technical knowledge, but also to find specific applications that could benefit most from that. And there you need some kind of experts that would you say what kind of specific information should be extracted from that 3D environment or from some spatial data that you have collected using these kind of sophisticated devices and algorithms. And at the end, when considering design, we would like to see what would be the final effects on the users and what would be the requirements they would like to have in these kind of systems. Of course, the users are always interested in some benefits like more profit, or that could be that could come from reduction of costs, yield improvement, or better planning and documenting of the work in the field. And that's very important if you have in mind that today agriculture usually they need insurance, and because you need to take into account different effects that you cannot influence, like weather or something else. So possibility to have tools to digitalize information about your work in order to have full documentation for some insurance company or for some grants is much better if you can have that. And what would be applications we would like to consider, like when speaking about spatial AI and use in digital agriculture? These would be like 3D, different kind of 3D reconstructions. You could do it on the level of the field. That's the second point here, like to estimate height of the canopy or its volume from some digital surface models. But you could also do it at very small scale, like to try to do some 3D reconstruction based on photogrammetry of individual plants in the field in order to have a better spraying or to do some kind of advanced phenotyping on the individual plants. And what kind of technology we could use, like on the larger scale, we would like to have some kind of scene understanding, but on the smaller scale, maybe only a few parameters that could be extracted from spatial environment would be enough for us to design some good strategies for treating these kind of crops or plants. One very interesting application that would also benefit from integrated design of these systems, for example, would be constant monitoring using some field data that are not collected from the inside of the field. But for example, if you have some kind of public transport, like bus services or people who are traveling near the fields, if they could have some cameras or systems mounted on their devices or vehicles, you could collect almost every day some kind of information about the environment that could be very useful for phenotyping or for mapping different kind of crops in some area. So that would be some kind of crowdsourcing collection of information, but in the field, you would probably be more focused on some kind of traits that are very specific or useful for your agricultural production. So when we talk about spatial AI, we should consider these kind of questions. And because here we will also have a panel dedicated to digitize anything. So today we are talking about digitalization in general. We could also say that spatial AI would be very useful technology and a tool for designing different kind of simulated environments that would be as realistic as possible, because if you collect this kind of spatial information and put them into some kind of simulation system, then in that simulation system you could design different kind of robots, machines, or consider some scenarios that wouldn't be possible in the reality, but could be simulated, and in this way you could make the development process much easier or better in case of some specific applications that will benefit from this kind of data, like spatial data collected by spatial AI. So that would be a short presentation or kind of presentation of ideas that would engage some discussions today and tomorrow. And I would like to hear your questions, and please come to us. And if you have any question or something to discuss, we would like to do it with you. Thank you.
Thank you, Branko. Is there any questions from the audience or online? And participants?
There is one question.
Yes, thank you for the presentation. Since you're computing like in real time or on the edge, how do you transfer the data or the information that you get on the drone, for example, to somewhere where it can be analyzed or used for the actions?
Yes, thank you. Very good question. There could be different strategies depending on the application and how would you use that kind of data. So if you would need it immediately to make some kind of good decisions, then you would need to have some kind of gateways or radio communication. But in most cases, you can do it offline, like when you come from the field. But it's important probably that you have it regularly, or that you do it with some plan. Because today, when you do some kind of advanced analysis or imaging, it's relatively costly, and it's not done regularly. So that's the main problem you would face, like when designing these kind of systems, how to provide not so expensive solution that could be used regularly on daily basis or weekly basis. And in that case, you would transfer the data or the results after you come to the base or to from the field, and that would be the answer.
Thank you. Thank you. So this presentation, it's now on our schedule about project from RedPTI will be later on schedule. So we call now Mr. Tjark Schutte from ATB to present us. Please.
No, sorry, we have but not yet. Sorry, we have another presentation before that. So instead of RedPTI's presentation, which is being moved later in the program, we are now going to have a presentation by Maria del Mar Plaza Cano from the University of Valencia. Thank you.
Well, good morning and welcome all to my presentation on internal PAE about human-aware robot control. This PAE has been carried out by Paco Blanes, my colleague, who couldn't assist today in person, and I, Maria del Mar Plaza. We are both from the UPV team and did this project in collaboration with the POSIX company. Oh, sorry. Thank you. Under the project, under the SMART4ALL project. The main purpose of this PAE is to develop innovative applications of IoT systems and robot control interoperability in industrial environments to improve safety in human-robot interactions and enhance resource efficiency. For that purpose, we have installed in our laboratory a ultra-wideband positioning system from the POSIX company and evaluated the data collected. The data provided by this location system, should be integrated into the ROS architecture of a mobile robot to deploy industrial applications. Both to improve safety in industrial environments and to improve resource efficiency, as I have said. The the ultra-wideband based location system that we have implemented in our laboratory consists on the elements that are shown in this slide. On the one hand, the tags are the mobile devices whose position is to be known by sending signal pulses to the anchors. On the other hand, a network of anchors receiving the signals emitted by the tags. And finally, a gateway that receives the information provided by the antennas and converts it in positions. The gateway is the positioning server that enables connecting the POSIX web application and robot modules to access using an MQTT protocol, as we can see in this slide. This slide shows the accuracy we can obtain by employing this ultra-wideband location system in our laboratory, depending on the signal coverage. In most cases, the positioning error is almost despicable and around 20 centimeters in the worst case scenario where the signal is weaker, as we can see. And we decided to apply data filters to reduce the signal noise and to get cleaner measurements. For example, as we can see in the picture on the right, the measurements are better than the first one. So it's more adequate to develop industrial security applications. The location data that that ultra-wideband system provides should be integrated into the RB1 robot provided by Robotnik company. This autonomous mobile robot can transport loads up to 50 kilos and has up to 10 hours of autonomy. This RB1 robot worked with a ROS architecture. It's like an open source framework that provide operating system services such as hardware abstraction or low-level devices control, among others, as we can see in the slide. And it works as the right picture shows, but I don't have much time to explain it. So in this final section, I will describe the application we have developed to improve safety in the work environments where coexist human and robot, and how we have developed another application to improve optimization of trajectories to improve the resource efficiency. The first application is the avoidance of obstacles in the work environment that the robot cannot see with its physical sensors, as we can see in this video. We use a virtual sensor that follows the same data structure as the laser sensor that the robot has implemented. This virtual sensor provides an additional layer of security for tracing pre-collision trajectories, which can contain reflective objects or any other object that the robot cannot see with its physical sensor. And the second application, using the same virtual sensor as I explained, to optimize the trajectories. In this case, the robot doesn't need to position itself in front of the object to know that there is a a barrier in its route. So it can progressively replan its route without having to backtrack at any time. And this application avoids time and energy consumption. So it is always better for us. As we, I didn't put the video, sorry. This is the video. The robot knows before arriving to the object that that is not the optimal route. So she replan the trajectory to achieve the goal in an optimal way. And as a result of this PAE, we will submit the ROS module developed and the instructions for use to the marketplace. And that's all. Thank you for your attention.
Thank you very much. Are there any questions?
Thank you for the presentation. A quick question. This solution can be applied to other robots using the ROS architecture, and or is it for specific devices, let's say?
Yes. All robots that use ROS architecture could be possible to apply.
Okay. And another one concerning the optimization of the route. Are you using a specific routing algorithm, or how do you?
No, the one that uses this mobile robot in concrete, but I don't know what type of algorithm is it. I don't know.
Thank you.
Thank you.
Yeah, thank you for the presentation.
Thank you.
I was wondering if you have tried doing it with dynamic obstacles. So if I think about a warehouse where there's several robots moving.
Yes. For example, when humans use the mobile tags wearable and they are walking on the laboratory, the robot knows in real time where the human is it, and without need to know without the need of what the human. So it is only with a mobile tag, and you can wear it wherever you want. So it could be dynamically used too. It's no problem.
Okay, thank you.
Thank you. Thank you very much.
Thank you.
So our next presentation is from ATB. Here, please.
Thank you. Okay, yes. Thank you for this opportunity, and yeah, I will try to keep my my presentation short. Also, our project is so far still in preparation, so I can't even present any real results. Yes, okay. Do we have those slides? Oh, okay. Oh, yeah, thank you. So yes, my name is Tjak Citte, and I'm from the Leibniz Institute for Agricultural Engineering and Bioeconomy. And I'm from the research group of automation. So we concern ourselves with also with robotics, agricultural robotics, a lot, and automation in agriculture. And yes, as we have seen before, one of the main problems of robotics is localization and navigation. And I'm not going to dwell too much on localization in this time. What we see right now in agricultural robotics is that most of the time it's done using GPS. And we have a special case where it's in wine production, where actually a map is generated beforehand using a handheld mobile device, GNSS device, in order to have the positions of plants. And yes, somewhat related to what has been presented before regarding spatial data in agriculture. What we want to do is we want to use UAV or drone data imagery to create 3D models in order to provide, firstly, provide a map to robots, to agricultural robots, and also be able to analyze in how far are orchards that we or farmers, if farmers want to use robots, want to robotize, in how far are the orchards suited to do that. And the idea is using photogrammetry, and like this is basically just jumping ahead. What a result might look like. I'm not sure if the video works in order to have it in 3D. Apparently not. Okay, but no, it's stuck. Can you? Yeah, okay. Okay, then I'm just gonna quit the video. What we can do by this is using such 3D models based from photos taken with a drone with commercial grade cameras. Actually, we can analyze orchard characteristics, analyze the suitability for automation and robotization, and we can also generate precise orchard maps for robot navigation and localization. And another thing, and that's interesting to our partner in this case, is we can, before we even go to the real orchard, we can simulate like robotic interaction in a 3D representation in a model of the orchard that is from its dimensions very close to the original one. So we can test algorithms before deploying them on the field. Okay, so to sum it up, what we want to do in this PAE is to integrate the 3D modeling technique that we have developed at ATB into the existing simulation solution of our partner. And then, and this is going to be a bit deeper technically. If you want to know more about this, please contact me after this. We want to analyze in how far we can do use this model that we have, the 3D data that we have, in order to have a self-supervising particle filter. So a localization based on, for example, LiDAR scanners or 3D stereo cameras that actually can validate its own results by running a digital twin in the background. Yes, and that's already it from my side. Yeah, if you have any more questions, I think we will have time throughout the day. Yeah.
Thank you very much. Are there any questions?
Regarding this second bullet here, digital twins, like this is related to simulated environments I was talking about. So what would you say in the perspective, how often this kind of approach for design of different systems will be used? Could you comment on that?
That's a good question. Well, the thing is, at the moment, what we do not have right now is safety certified, like especially in safety critical systems, we do not have safety certified solutions for localization. Apart from maybe GNSS, some GPS systems are up to a certain degree of certification, but we do not have a SLAM algorithm that is certified. So the question is, can we get to a point where we get the system to be certified? If that is the case, then it will be very interesting. But that's the second part of this project, and it's more like an outlook.
Thank you. Thank you. Some information before we pass on to the next presentation. Presentation of the Smart for Women network is postponed for tomorrow, and the presentation after the lunch break for presentation of the virtual incubator network initiative is cancelled. So now we go to the presentation. Mr. Radovan Stojanovic.
Can I check? Okay. First of all, I always like to come in on time because there are several things. About the programs about all stars coming from Novi Sad, from all generations.
Radovan, sorry. If you stand there and don't use microphone, people can't see you and can't hear you who are online. So please, you're off.
It's not necessary microphone.
Yes, it is, because people who are online
Okay,
can't hear you.
okay, I will take. Because of all people from Novi Sad are very, very skilled in the products. They have good professors, good students, good environment, good startups, good people, initiatives, and so on. They are really mega stars in the project's implementation in Western Balkan. The second one are coming from the Greece. The place in Greece that is the, let's to say, one Silicon Bay of the Greece is Patras Bay. And all the people here are, as you see, Christos, Nikos, me, are coming from the same school. And there is one sustainable cooperation extracted to the region. That I expect also from these projects to have future and many people interested in future cooperation, in future projects and so on. It is not only temporary money. You should to see indirect values. You should to see what those people brought to the area, brought to the development, brought to the country, and so on. I am coming from University of Montenegro, and we worked with University of Novi Sad many projects. Some of them are missionary projects. But now I will present in front of MECONET. What is mean MECONET? Sometimes you are implementing the best projects with nothing. If you ask me, what is ratio of quality of the projects will not be proportional, will be inverse proportional to the money of the project. The best projects are with the less money. And we establish one MECO, Mediterranean Embedded Computing. And MECO 1 is now the first conference in the field of embedded computing in the world. Officially in the top conferences in embedded computer, cyber physical systems, Internet of Things. And to this conference, we had a lot of additional products, summer schools, initiatives, and so on and so on. Later, we did instead MECO, Mediterranean Excellence in Computing and Ontology, because it is computing, it is not all. We are speaking about technical details, we're speaking about some small details, but are nothing in the project. Those are, let's to say, for daily use. Projects should to have vision, should to have direct, indirect values, and we will see on 10 years, 20 years, what will be with the project. And well, ontology means that we are most implementing social sciences, technical ontology, other managerial aspects in this sense. I will speak about some partnership for these small experiments. What is the problem? How we need to solve this problem? How we go to solve this problem? What is way to do to solve this problem? Example, more about and conclusions. This is the problem between two companies here, Meconet. It is Murphy law. Someone is calling when I have presentation. And the one is Meconet, and the second one is ProSmart. It is about some wearable health device for detecting COVID. The name of this device is Syntrophos. Syntrophos in Greek language means follower. In our language is pratilac. What it means, I will not bore you about technical details, what is job of one company, the second company, and so on. The main idea is to have one smart mask, and this smart mask to detect some parameters, vital signs, interesting for the COVID. Because the mask is very useful to detect some vital signs. Then also to have some earphones had like sensors like you have with your mobile phone, and everything to be like one earphones with mask to detect vital signs. And now I will not bore about this problem. You should to know that some vital signs from medical informatics, biomedical engineering are very important. First, oxygen concentration. Now we see what means oxygen. Or nothing without oxygen, no life without oxygen. Saturation of the oxygen in the blood is the first parameter showing are you have critical symptoms or not. Then respiration rate, your heart rate, and so on, other parameters. And we were able to detect these parameters for these head-like sensors and the mask. You can see here some preliminary research. This Syntrophos is made already ready in some, let's to say, gadget version. You have the sensors and you have the iPhone or some, let's to say, mobile device, and it is for some, let's to say, the second step, not standalone configuration networked that you have everything in these smart watches and so on. The second configuration will be easy integration. Easy integration will be done by ProSmart company. You heard by the Christo about these beacons. And the beacons are all around. We have for everything beacon. Now someone for me through my beacon and so on and so on. And we like to connect our mask, intelligent mask, COVID mask to this beacon. And this beacon to be now some interface or gateway between hospital system, remote doctor, your family, and your parameters. Should not be this case should be easy from agriculture, no matter. And this job is done by this ProSmart company. How to do it? You can do it by deep and eye approach. What does it mean? Do it in the place and integrate. What it means in the place and integrate. We are not able to produce microcontrollers. We are not able to produce FPGA platforms. So we are not used to produce chips. Forget it. Sometimes I have some dreams to do some laboratory to produce chip with my colleague Veljko Milutinovic and others. Those are our dreams in the Balkan. We are not more able for this. Only what we can offer is knowledge. Knowledge of the middle generation, not knowledge of the new generation. The knowledge of the new generation is not enough for some peaks. Forget the knowledge of the new generation if we do not improve it. And only to sell the knowledge. What it means, some algorithms, some deep learning, some artificial intelligence, some mathematics, and so on to implement these chip platforms. This platform can be system on chip, system on package, and that's it. That's all. And here our partner is implementing algorithms on the chip and the platforms. There are many names: embedded computing, cyber physical systems, artificial intelligence, big data, and so on. Everything is trick for the same different name. In my time and time of college was neural network and such artificial intelligence, but was not able to implement this neural network on the chip. Was not power. Now it is really allowed, and we should do it. And this partner is doing it. The other partner is doing hospital information system and remote doctor orientation systems. And I will tell you some example. Even in this small chip, even in this small chip of €2, you can implement very sophisticated signal processing algorithms to detect several critical COVID parameters. And everything is interfaced on some small chip. Now, I will not go in the details about signal processing and optimization. We don't have time for this, but it is mathematics in time, in frequency, in time frequency domain, and extraction of some parameters. For me, old school, those are tips and tricks. Those are tricks, but believe me, those tricks are now big mathematics, big papers. One of my friends took the books from the pillar and they made the best papers. And you can see even in some chip of €2, we can implement sophisticated Fourier transform and extract some peaks that is important for our job, respiration ratio, heart rate ratio, also this, how we say, oxygen saturation, and so on and so on. And everything is working in some small chip with small amount of the memory, and everything is done in place with some mathematics tricks and so on. Even you can put to find oxygen saturation in this small chip, and so on and so on. More about those are in some publication through our projects. You can see some publication from side from Greeks, from side of my research groups, and so on. There is one excellent, the best summer school in Europe. I do not have any from the Balkan, but it's kit in the Scandinavia USA, and others. Every year is in Budva. There is a summer school on cyber physical systems and Internet of Things. From ETH up to the best universities. In region, no one is interested. Believe me. And if you go to see these proceedings of this summer school, then you will find very good lessons about those things that I'm speaking, not those things, from edge computing up to other thematics lessons from the teachers. And try to find those. Please go on the other side. Conclusion, we did such system, design philosophy that I described to you. The principle can be extended to different applications. Why? Technology is capital and one Coca-Cola is the good. Knowledge is capital. I use the knowledge to take many projects for the same thing. You can sell the same trick in 10 projects. What it means? It is a capital, knowledge capital. You cannot sell one Coca-Cola 10 times, but you can sell your knowledge 100 times. One time in precision agriculture, the second time in health, the third time in the social inclusion, the fourth time in psychology. That is one advantage of the products. Then my recommendation is do not try to drink water from the hydrant, because today is too many informations, too many projects, is flooding of the data, is flooding of the everything. And can you imagine one man that should try to drink from the hydrant? Never will drink. But it is possible if you use some tricks. Other time I will tell you how to use, how to be even to drink even from the hydrant, and to have idea how to use those money for some useful things. The products are good because it's money, foreign money. If you use this foreign money for good purposes, working on yourself or your community, then you succeed. If you using money of the products because of the money of the products and products, nothing. Remember why Jewish people are very, very rich? They always work with foreign money through the banks. That is one invitation of them. That is from me, and I am very, very glad that I'm here. Also, Boris and Zoran are, let's to say, very good persons in preparing meetings and so on. And every meeting in Novi Sad, even being small one, is very well prepared with a content idea and good presentations. Thank you very much.
Thank you, Radon. We now go to a lunch break, and after that, we'll resume at 2:45 for people who are online. We have 4 sessions at the same time for 4 different parts of our project. So please choose one of them, or try to switch between them to see what is happening then. Until 2:45. Bye.